like week after week. Thank you. Week after week, it's incredible to see everybody coming back, see all the participation, also seeing some new faces. So yeah, just again, want to say thank you for making the time and for making this kind of a group experience. It's really important. So without further ado, I'll get into it. And I won't be talking for long because we are joined today by Gregor and Florian from Ov1 Labs, the company that incubated Mina Protocol and is building Snarky.js. So they're going to give us a presentation on zkApp architecture and some decisions using decisions around architecture choices using a real world example. And then we're going to stay for a Q&A, so you will have some opportunity to ask questions. And then we're just going to finish with a little bit of info about next week. So we're really, really excited for that. But to start, really pleased to share that we've gotten 107 zkApp proposals, 64 dev for dev proposals as of the draft deadline on Monday. And this definitely is an amazing start to zkIgnite as a whole. Like just the amount of ideas and brainwaves and collaboration that's already happening to kind of get to this point is really special. So I just want to give everyone on this call and everybody who's contributed a shout out. We're now in the revision, the feedback and kind of revision phase, where you'll have another 2 weeks to seek feedback, comment on other proposals, potentially continue to work on those on your own proposal based on feedback or just based off of your continued, continued work on it. And the revision deadline will be March 21st at 11:59 Pacific time. So the very end of the day, West Coast time in the US. And so you'll, even if, you can expect to kind of receive feedback, understanding that maybe your proposal might not be final. But as this is like a really integral part to cohort one, when we're getting into this phase, not just like everyone submitting a proposal, but also figuring out how to leave feedback and help each other out. This stage is super important, and we're really, really, just again, grateful to everybody who's kind of being generous with their time and their energy when it comes to helping other people succeed here. Again, really excited and while not all of these proposals will get funded as part of cohort one, we'll have cohort two, we'll have cohort three, and there's other ways to get involved, which I'll talk about in a second. But this is an amazing start, and I'm really, really, really excited about what the outcome is going to be in terms of, building the ecosystem from the ground up. Okay, we've gotten a couple questions around when do I get feedback? Where do I go to get it? And I'll answer that question with the famous Spider-Man meme. This is, if we go back to what a Cambrian explosion, the goal of being a Cambrian explosion of zkApps within the Mina ecosystem, it really comes from this, collective energy that we're building as part of this program. And while we are on the Mina Foundation team are facilitating this, we're trying to kind of provide that test tube environment, test tube energy. I don't know if that's a weird thing to say, but this kind of environment where people, the feedback is really going to come from your peers and your collaborators and your other people who are within this zkIgnite. There's lots of people who are building tools that will be interoperable with one another, that are actually be dependent on one another. And we want to, as Mina Foundation, want to provide this environment for you to be able to go out, seek that feedback, potentially set up even initiatives within this program that allow other people to give feedback. And we're very, very open to ideas around what shapes this could form. Next week, we're going to be doing actually presentations, and that will be a little bit more of a formal opportunity to ask for feedback. And Janae will talk about that at the end of this call. But in the short term, we're going to be opening up Gather after this. We're also going to, potentially be open on the Discord. If people want to organize their own sessions for getting feedback, we're happy to open up the Gather Town for that as well. Because we've gotten over 160 proposals, there isn't necessarily a super easy way to organize feedback for everybody right away. But what we are going to commit to doing is providing the space and providing the kind of just the message to the group that feedback is supposed to come from within. and to continue to kind of offering feedback just as you might be expecting that feedback, because again, there's so many interested people here with a lot of, a lot of investment in the outcome of the Mina ecosystem. And so I think it's best for everybody if we kind of approach this with this giving mindset when it comes to feedback in a constructive way. Okay, so just want to send, a reminder, and just kind of like, because we do have so many proposals, like not, it's impossible to fund every proposal as part of cohort 1. And so other ways to possibly contribute would be, leaving feedback and discussing proposals, joining a team. We'll shortly be opening up kind of a job board on the platform where teams will be able to actually offer more formal positions other than just reach outs. So more to come on that. We have 1 week left where you can apply to also become a mentor if you'd like. And the link is here. Well, you can also check out the link on the platform. If you see projects that you think are really interesting and you want to spread the word about them and kind of like help them along their journey, we encourage you to share on Twitter as well. I've seen some people do that as well already. Shout out to Robbie, who's been doing that on Twitter, who's a longstanding member of the ecosystem, and it's been cool to just even see when one person shares it, you never know who's in their network and who might want to be a user or a tester or potentially even join their project too. So sharing is caring, and it's not just about only submitting a proposal and getting funding. There's a lot of other ways to also contribute as part of cohort 1. We're also thinking about we're observing all of the activity that's happening as part of cohort 1. We are kind of like taking notes on how these contributions are working, and we're going to kind of like think about who's contributed and how they've contributed when we're designing roles for cohort 2 and cohort 3. This is we're still in this phase of experimentation. So as we're thinking about electors for future rounds, as we're thinking about mentors for future rounds, we're paying close attention to kind of like how this collaborative environment is working and who's really standing out. I could even see there potentially being some sort of like a leaderboard format in the future. We didn't want to overcomplicate it for cohort 1, but again, like this is all the effort that goes into cohort 1 will then result in kind of how we structure cohort 2. So it's important to kind of think about it in that way. And speaking of cohort 2, we're going to start thinking about more formal dates and how to kind of translate all of this positive energy that's happening right now into a more longstanding, program. We've talked a little bit about cohort 2, cohort 3, but stay tuned because we're gonna continue to put more details around that. Okay, I also want to give more shout outs. These are just people who've been super active on the Discord, super active in the comments section so far. So shout out to everybody here. I am Dev, Altoid, Cold Star, Zonu, Yamakan, Flush the Fashion, Narendra, Yukin, Jonas, the dude, Nintran, Adenomics, Harvardyac, and Mario Zito. There's many more people that will be on this slide. We're going to do this every week. Just want to give a shout out to everybody who is kind of like going above and beyond and contributing on the Discord and both in the comments. And again, that's what makes this program successful. Okay, so without further ado, I'm going to pass it over to Florian and Gregor, who are both engineers on the O1 Labs team, the team that incubated Mina Protocol, and I'll pass it over to Florian first. Florian is also a longstanding member of the Mina community. I'm sure many of you already know him, and really excited to get into it here. So Florian, I'll pass it over to you.
Yes, thank you very much. Let me just very briefly share my screen. Let's see. Oh, that should do it. Okay. So thank you for the introduction, Bill. Today we will sort of like go over the architecture of zkApps, and we will like use a voting app example, and we will gradually progress from very easy to like a more advanced system. And by doing so, we will like sort of explain how you can structure a zkApp, what it may look like, what sort of features you can use, how things play together. So again, we will like learn how to design a zkApp, and then explore the different life cycles from like a first idea to maybe a proof of concept, and then do like a final business idea to like sort of like a real system people can use. There will be different modules and parts of zkApps, and we will sort of demonstrate how they play together. And we will again advance in difficulty. So we will like go from relatively easy to like a more advanced level at the very end. Just to like sort of manage expectations, it is important to mention that we will not show you how to like develop a smart contract. We also will not present you with like a finished application, a finished product, and we will also not really explain any implementation details. Just simply because this is not a tutorial or a guide. We have like many of those. And if you sort of like need direct support, there are like sort of venues where you can go. But this is overall to like demonstrate how you can make design decisions, architectural decisions from like a high level, and how you can approach your problem for like from a more abstract point of view. So we will look at a very specific use case and explore this use case. But what do we want to build? We will start with a relatively basic voting application and then add more features to it until we have like a sort of like pretty decent application, a large system where there are many modules playing into each other. And we will jump straight in with a very easy on-chain variant. So I wrote down a sort of like a problem statement, something that you may want to build if you have like an idea for zkIgnite. So we want to build an on-chain voting smart contract in which a voter can vote for a unique proposal with either yes, no, or abstained. And another thing that we want to have in our application is that voters should only be able to vote once. So for each of those sort of like states of our application, we have drawn diagrams. At each of the sections, the diagrams will be shown at the beginning of the section and at the end. It's just sort of like to show you the progress, introduce you to what we are doing, and then at the end, we will go through it again in more detail and explain how the diagram requirements and problem statement. So at the moment, you shouldn't really think about the diagram, just like take it in, just like a brief glance, like think about it, but already forget it. Because now we are sort of like going to isolate the requirements from our initial problem statement. And we're going to start very basic. We want it to happen on-chain and it should be public. It should be like a public vote. And again, voters should be able to submit their vote and vote for a very specific proposal with either yes, no, or abstained. And in addition to that, voters should only be able to vote once. Early in the diagram, we already saw a nullifier. So a nullifier is a primitive that we will need in order to keep track of who has voted and who hasn't. It sort of allows us to like prevent people from voting multiple times or like causing double spending in like applications, tornado cache mixers, for example. There are a few different constructions of how nullifiers can be built. For now, we will simply assume they are a black box because again, we are not going into any implementation details. If you want to learn more about nullifiers, you can just simply click on the link below. And you will see that throughout the presentations, there will be a couple of those highlighted sort of like texts at the bottom of the screen or in between the slides. And at the end, when you get the slides, you can just simply open them and click on the links if you want to learn more. So we sort of like accompanied every other slide with like a few more resources if you want to learn more. So if we consider our architecture of our zkApp, we will need to store 5 field elements on chain. We know that we can store 8 field elements. At the moment, we will only utilize 5. So we are starting with 3 sort of like accumulators, variables that store votes. We will have a variable yes, which stores all the number of yes votes. We will have the same one for no and abstained. Then we will have another field called proposal ID. This is simply to like keep track of what proposal we are voting for. Are we voting for a DAO proposal? Are we voting for like a leadership election, whatever? So this is like just something to keep track of our sort of like where the votes belong. Then we will have a nullifier root. And again, the nullifier is sort of like a, we will treat it as a black box. It is just important to know that it exists. And because our smart contract is very basic, very simple, we will start only with one method, and the method will be vote, which sort of means that a voter can invoke the vote method, provide a choice, the choice being either yes, no, or abstained, and then a nullifier. The nullifier is provided by the user in order to prove to the smart contract that the user hasn't voted once before. So it's sort of like a replay prevention. We declared a very basic interface to sort of like take the architecture that we just went through and to put it a little bit into code, something that you can read and maybe understand if you're a bit technically. We have, again, 5 on-chain state elements that you can see on the top. And on the bottom, we have a very basic the vote method. So the end-to-end flow of our application will, again, be very simple because our application is also relatively simple. A voter would simply start by invoking a smart contract method on the client side. That could be either directly in the browser or using like a Node.js script, either way, client side, and provide a valid choice. If the user, then the user has to provide a smart contract with a Merkle proof to the specific nullifier, which is the nullifier that we spoke about earlier, in order to prove that the user has not voted before, because we want to prevent double voting. The smart contract will update the on-chain state if the proof is valid, and depending on a few sort of like preconditions. And the smart contract will update then the like sort of on-chain accumulator of the different types of votes, yes, no, abstained, and will sort of like increment them every time a user invokes this method. So, and now just to go back to the summary of the very basic smart contract, maybe it now makes a bit more sense if we start reading the diagram from left to right. We will start at the left side where the voter is, and the voter would simply interact with zkApp, and zkApp being on the client side in the browser in Node.js, and would then generate a proof of their method invocation, and then send that proof over to the on-chain sort of like smart contract, which lives on Mina, which does the verification step and then updates the state accordingly. And then on the top left, we will see that we also provided nullifier tree. And in here, you already have like some sort of indicators indicating whether or not an entity has voted before or if the nullifier is empty. And we use this to prevent double voting. And this would also be an input to the smart contract. And the next 2 steps are sort of like building up on this. We started very basic, very simple, only one on-chain smart contract. The user interacts directly with the contract. And in the further steps, we will sort of like keep adding functionality and adding features so that we like can see how this application grows. And for that step, I'm going to pass it over to Gregor.
Thanks, Florian. Okay, so yeah, can you move to the next slide maybe? So this next step will present a more slightly more advanced example, but still not too advanced. So we will stop addressing some of the problems in this first version. Maybe you noticed them. So one problem is that there's no restriction at all on who can vote, and probably most applications want to have some restriction on that. So we want to have a way to say how who can actually vote and verify them. And the next problem is that in the current design, we do everything in one transaction. So the user updates the state of how many votes have been casted for different options. All of this is updated in one transaction, and that is a problem usually in zkApp or on Mina, because when we do that, we need the earlier state. So we need information about. Okay, say we update the number of yes votes, then we will so zkApp will do this under the hood. We'll fetch the current number of yes votes on chain. This will be taken from the last block, and then we will set the state to that +1 if we voted yes, for instance. And to make this secure, we set a precondition on the state. So this transaction will only be accepted if the number of yes votes is exactly the number that we said it was. And then it's set to that plus 1. Because if we wouldn't have this precondition, we could set the votes to anything. That would be not good. So we could set the number of yes votes to whatever we want. So that's why we need this precondition. But the precondition is also a problem for concurrent usage of this smart contract, because if one user does this and says, okay, this transaction can only, if one user votes yes and the number of yes votes is changed, and the next user comes along, he will still use the old state from the last block for his precondition. So the precondition will be outdated, and the transaction will be rejected. That's a very common problem when you have on-chain states that should be updated concurrently, multiple times in one block. And we have this problem here. So in the current architecture, only one vote for each of the options could be successful in every block. So that would be a pretty slow voting contract. We would just go one vote block by block. Okay, so how do we address these things? So the idea for the first thing, verifying voters, was we will allow only voters with a certain email address. So for example, only if you have an email that ends in 01labs.org, you are eligible to vote. So this could be used by an internal zkApp from 01, for instance, if we wanted to vote on something internally. And the second, we want to support concurrency. We want to support multiple votes that can be cast in one block. So these are the two new requirements. Next slide, please. Okay, so here's the solution at a high glance. What we'll do is we will introduce an oracle, and this oracle will provide us with the verification that we have a certain email domain. So this is the blue box that was added here. And the other part that changed is if you look at the snarky.js, at the smart contract, then we now have two methods. One is cast vote, and the other is count vote. So there are two different steps now. Step one is we just cast a vote and emit that as an event, and there's a separate step that counts the vote. That is how we will get by. This is how we will prevent this issue with concurrency, that we separate this. Okay, so let's see in more detail how this works. So instead of voting directly with one transaction, votes will be dispatched using actions and will be reduced at a later step. So this is the separation between cast vote and count votes. And in addition, as I said, we will determine voter eligibility by an email oracle. Okay, let's dig into the details of that. So what is an oracle? Oracle is a common term. It's just something that provides your smart contract with some data, with some external data from the real world. In this case, this will be an email server, and it will give us something that we can use, that we can put into the smart contract. So in this case, it will give us a signature of some kind that we can check in a smart contract, and then be sure that the current user can use this method. So so the oracle will be some kind of server which can receive emails. It will send back a signature, and it was also important is that the user. So you will send an email to this server, and it should include some commitment to your public key. Okay, so in that way, your public key gets connected to that signature that you get. So the oracle checks that the address ends with some domain, some specific domain, and it will sign some statement that's saying, I don't know, public key, okay, whatever. It will just sign your public key, and we will send that signature back to you. So and this signature now says this user has this domain. So the verification step was that you were able to send an email from your address. Okay, now to the other thing that we want to fix. I said that we wanted to cast votes as an action. So what are actions? Actions are kind of events that are supported by Mina. They can be dispatched in a smart contract, and they are not stored on chain, but a hash of them is stored on chain. So there's a chain of hashes. So actions form a list, or are the actions ever dispatched, and they are hashed into one thing. It's called a Merkle list, and this is the commitment that's stored on chain on your account. So if you actually know the actions that one account dispatched, then you can check that. Then you can check that these are the right. You can check it against the hash, so you can prove that you know the correct actions. That's what make them usable in smart contracts, because in zkApp we expose this as a reducer, which can reduce your actions. So it's like reduce in many languages, and in JavaScript, for instance, there's array reduce, where you have an array and you can pass one function that takes some current accumulated thing and a new element and apply some function on it on the entire array. So that's I don't know, it's like the most flexible array processing method that you have, and you can use this to process actions in a smart contract. So okay, and how do we use this? When we cast a vote, we won't directly mutate the state that we actually want to mutate. For example, the number of yes votes. Instead, we will just emit an action which says yes, voted for yes, and my public key. And there's a separate method that runs reduce on all the current pending actions and counts them up, counts up the yes, no, and abstain votes. And in the link, you can find more about actions and reduces. So our architecture is similar to before. There are just two differences now. The one new thing is the oracle key. This is the the public key of the email oracle. Remember that the oracle signs something, and we want to check that signature in the snark. So this is the public key that we want to check the signature against. So this is the trusted public key that we know will sign messages correctly. And we have now two methods. Cast vote is what a normal user would call, and count votes is an extra method that handles the reducing step for us. So yeah, and other parts of the architecture. Okay, there's a list of dispatch actions that start in archive nodes. In our case, this will be a list of the pending votes, which haven't been counted up yet. And so this is built in within our frameworks. You won't have to deal with this, but it's still part of the architecture. And the same for the commitment to the committed actions. So this is just architecture that's part of Mina already. Okay, next, let's look at what we have to do to make this happen. So in the new Oracle key state should probably be a public key, not a field element, but I don't know, doesn't matter. The new cast vote method now takes not only the choice and the nullifier, but also the Oracle signature. And in the method, we have to verify the nullifier, and also I have to verify the signature. And we verify the signature against the Oracle key, the public key. And then we dispatch an action which contains how the user voted, who the user is, and also the nullifier, actually. Should also be part of the action. And the second method, count vote, this should reduce the list of pending actions and update the result of the vote. So this will update yes, no, abstain. Okay, next slide. So, okay, I said most of this now. We send an email to the oracle. Okay, next. So when the user invokes the voting method, okay, this could you refresh? Okay, I changed this a bit because I think the nullifier should also be part of the action. So the smart contract will verify that the nullifier is valid and that the signature matches the voter's address. And an action is dispatched, which includes the choice of the voter and the nullifier, but it won't change any state. Okay. And when the count votes method is invoked, it will go through the actions. It will count the votes, and at the end it will have a result, how many new additional votes or something, and it will update the state to that. So that's how we separate state updates and user interaction. And so we achieve concurrency. And what the count votes method should also do is this will check that the nullifiers are not set yet. And it will also update the nullifier root. Because if we do that in the other method, then we again have this problem with the state precondition. Okay. Yeah, here's the diagram again. Maybe it makes more sense now. So you can see, yeah. makes more sense now. Florian, you're next.
Yeah, thank you. Thank you, Gregor. So now we will sort of like take this entire voting application off-chain. So instead of like doing the voting on-chain, either with or without actions, we will do the voting off-chain and only sort of like verify the result of the vote. To define a problem statement, in addition to all previous requirements, like no double voting, for example, and we want to have the email oracle, we now want to scale our application further by aggregating votes off-chain using recursive proofs. And we still want to maintain privacy and anonymity, and votes should only be casted once. So as you can see, the diagram is now like slowly growing from the very easy application that was just a very linear sort of user flow, a very linear diagram. You can now see that we have like different parts, different modules, all sort of like interacting with each other and like requesting information from each other. And so, yeah, it's sort of like growing because we are also now going off-chain. One important part to mention now is that we now have two snarky.js sort of like spaces. On the very top, you can see something called zkApp recursion. And on the bottom, again, we have our smart contract part of snarky.js. That is simply the part that we like used in the two previous examples. But now we just have the zkApp, the recursion API as an additional sort of like module. So to recap the requirements, so for improved user experience and better scaling, votes should happen entirely off-chain using recursive proofs. And because we go off-chain, whenever we go off-chain, there's sort of like the notion that we use privacy and anonymity, but we still want to make sure that that the system is still private and anonymous. So one very important part is votes should only be revealed at the end of a tally. And there should be no central authority that has access to the content of the vote at any time. That just means that if there is a authority, like a tally authority who's counting all the votes, they shouldn't be able to see what the votes contain. That means, is it a yes? Is it a no? Is it an abstain? Are you like voting for a specific person? That should all be hidden. To now like sort of explain the different modules, like you saw before, we are now introducing something called zkApp. The zkApp is, we sort of like define it as our recursion API in snarky.js. It allows you to like verify a proof inside another proof. So you like can recursively verify proofs. And with this zkApp API, we can write recursive proofs, which can be then verified either directly off-chain within another recursive proof or verified in the Mina smart contract. And what that does is it is enabling us off-chain use cases. So that's pretty cool. And if you want to learn more about the recursion API, the zkApp API, you can take a look at the docs. So for the architecture, and we are first going to consider the smart contract architecture of Mina. And you can already see that we sort of like decreased in complexity because we now have different parts. Instead of having like the nullifier root on-chain, instead of having like the oracle key on-chain, we now only have the result of the vote being yes, no, abstained, and only the proposal ID, proposal identifier on-chain. And we also only have one smart contract method. But we now have a different part, again, called the zkApp, which is sort of like taking care of the proving, but only off-chain. So there are now two methods. The first method being batch votes, which takes as arguments a proof and another proof. And it is used to recursively merge proofs. So what we do is essentially we take two proofs, we verify them, and it gives us one proof, which is sort of like reducing the proofs. The second method is called vote. This is the method that a user would invoke. The vote method, again, takes an oracle signature, a choice, and a nullifier, just the same as before. But now instead of like invoking that method in the smart contract, we are invoking it off-chain. And we are only taking a proof and then sending that proof over to an entity. Another important thing, we already touched on that, is the nullifier tree. Nullifiers are like sort of like check marks, like private check marks that sort of like say, okay, someone already voted, someone didn't vote. It's just essentially like a list of Boolean yes, no, that belongs like sort of can be traced to a specific address. We didn't mention that yet, but we are aligning those nullifiers in the Merkle tree, so we can like use the nullifier, sort of the proof of inclusion, to like redirect, but not so important. Another entity is the off-chain tally sequencers. The off-chain tally sequencers sort of like prove incoming votes from users, and they aggregate all votes recursively. So you can think of it like when you're voting in an election, you vote at a sort of like at a building, and then within there are like sort of tally authorities that each publicly count your votes. But you want to make sure that this is like private and anonymous, and also on-chain. So there's like this sort of off-chain tally sequencers. So to look again at the smart contract a bit like in code format, again, it's like very simple, because we now like split up the logic into off-chain and on-chain. And the on-chain smart contract is only supposed to verify the proof and update the final result of the vote and not do anything else. So this is relatively simple. And you can see that we have the verify proof method, which is taking sort of like the proof of the final result and verifying that, and then updating the state accordingly. But then we do have the second part of zkApp being the zk program, which is the recursion API. And here we can see that we have the two previously specified methods. The first one being batch votes. It takes in as an argument 2 votes and then sort of like merging them. And then we have another method called vote, which would be invoked by the user, which takes the oracle signature, the choice, and the nullifier. And within this vote method, we would again verify the oracle signature, verify the nullifier in order to prevent double voting. And then we would sort of like prove the choice. So again, this is only like a very shallow overview of the interface. There's like no implementation details in here. It's just used to like sort of like conceptualize what we are trying to do. And to like take a step back and sort of like explain the end-to-end flow and how everything works together, plays together, we would essentially start with the oracle, because we still want that a user can only vote if the user has a certain email ending with a domain. So the user would then go ahead and send an email to the oracle, and then in which he commits to a Mina public key, and then the user would get a signature by the oracle attesting to like that fact that the user indeed owns a certain email address. And we already spoke about that, so that's like nothing new, nothing is exciting anymore, but now we are sort of getting into the off-chain vote space. And again, instead of like going directly to the smart contract and voting on-chain, what the user would now do is go to the zk program API used and generate a proof of their vote locally within their browser, and take that vote and then send it to an off-chain sequencer instead of sending it to the smart contract. So the off-chain sequencer is also here treated as a black box. There are different ways how you can structure off-chain sequencers. They can be centralized, they can be distributed, they can be decentralized. So there's like a big list of options that you could do. I will go into like a bonus section at the end explaining how you can do that. But right now, we also just treat them as like a black box. And yeah, again, the sequencers will then go ahead, collect and receive all votes from users, verify them. After some time, if there have been like enough votes collected, or if we are at the end of the voting period, the sequencers will go ahead and aggregate them recursively until only proof is left. And at the end of the tallying process, the sequencer would then take this sort of like final proof, which has all the previous vote proofs sort of like merged into each other, and then send it to the smart contract. And when then the sequencer sends that final proof to the smart contract, the only thing that we have to do on chain on the smart contract is take that proof, verify it, and then update the final result of the vote. So you can now see that we went sort of like from a very naive approach to something that's a bit more complex. And we try to sort of like reduce race conditions and have a better concurrency model using actions. Because we have to like, we originally invoked on-chain smart contracts relatively frequently. Now, instead of like invoking 1,000 on-chain smart contract methods, the only thing that we do is verify one proof, and that's it. There's nothing else that a contract has to see, that a contract has to do. It only has to verify one proof. So if we look again at the architecture, it should now be a bit more clear. At the top, again, we have our oracle that is providing us with a signature attesting to the fact that a user is indeed the owner of a certain email. And then instead of the user going directly to the smart contract, it sort of like taps into the zk program, the recursion generating a proof, and then sending it over to the sequencers, and the sequencers then batch votes and verify them on the smart contract, and the smart contract then updates the Mina state. So again, we didn't really go into any implementation details, but now at the end, I just sort of want to mention a few things because they're important and very worth knowing if you're looking into building something similar, if you're looking into building voting applications or whatever. So any scaling that is happening off-chain with recursive proofs is sort of like being like every proof is being aligned in a binary tree, and every binary tree is sort of like one recursion step. And like the very top of the tree, like the root of the tree, is then sort of like the product of all previous proofs. And this method allows us to like take many individual voting proofs, merge them together until we only have like one proof at the end, which we then can send to the on-chain smart contract and verify very efficiently. And here you can like sort of see how what I mean by like aligning proofs in a binary tree. We can see at the very bottom at the leaves of the tree, we have our sort of like our base case, our proofs, each attesting to a different vote. There's a proof attesting to a yes vote, and there's a proof attesting to a no vote. And then if we take each two proofs and merge them using the batch votes function that we just talked about, we will get a new proof attesting not to only one vote, but attesting to two votes. So on the left side, we can see that we have a proof attesting to the fact that there exist two yes votes. On the right side, on the other hand, we have a proof attesting to the fact that there exists one yes vote and one no vote. And if we sort of like do this batching function again, we then have a result of having like one final proof, which attests to the fact that we have 3 yes votes and 1 no vote. And we can then take this proof and send it to the Mina smart contract and let it verify on-chain and then update the result. And then we know, because we trust cryptography and math, that all the previous votes were correct and the on-chain result is indeed valid. And then we update the on-chain state, and then the result, like the vote ended, and we have the result with 3 yes votes and 1 no vote. So this is a very, I guess, common pattern on how to scale proofs. If you want to learn more about that, you can take a look at the recursion and proof aggregation section in the docs. I also linked the docs again here on the very bottom, so you can just click on it. And we always sort of like talked about privacy and anonymity, but in fact, this is just an implementation detail. That's why we sort of like left it out. But it's still important to mention and talk about how you can achieve privacy. So at the moment, we are using a oracle to sort of like prove to the smart contract or to the off-chain recursive proof that we are the owner of a certain email address. We could also use, for example, Merkle proofs for that. By using Merkle proofs, we would define a set of eligible voters. That set could include, for example, all people who own more than 1 million Mina, for example, or less than 1 million Mina, whatever. We would then align those individuals in a Merkle tree, client all their values, and then every user would simply provide a Merkle path to the root, sort of like proving that the voter is indeed eligible to vote. Another big thing in voting is not only privacy, but also anonymity, which is sort of a slightly different thing. If we are going off-chain, we previously said that we don't want anyone to be able to read the votes because we want to like fully anonymize the process. And that means that the votes have to be shielded or like hidden. What shielded or hidden means is simply that if we have a proof and a vote, we are looking at the vote and we should not be able to tell what the vote is voting for. So we shouldn't be able to tell, is it a yes, is it a no, or is it an abstained? But when aggregating all those votes, no sequencer should sort of like be able to like see that content. Otherwise, there could be like possible attack vectors, like the sequencer could be able to track back votes to the voters on chain if there's like a big Mina account that has a lot of Mina and then therefore has a lot of vote bait. The sequencer could then take that vote and trace it back on chain, knowing that who voted for what, for example. So we want to like sort of hide that fact. Sequencers could also use this advantage to predict the outcome of votes. So for example, let's say we have a big vote happening and there's a bet off, like there's an on-chain bet that says, okay, yes, for proposal XYZ is going to win. And if it's going to win, I get 1,000 Mina, like sort of like a betting, for example, like horse races. So we may want to like sort of prevent that. And the solution, for example, is partial homomorphic encryption. So homomorphic encryption allows us to apply operations, for example, addition or multiplication on encrypted data. And as a result, because we can do that, we can encrypt each vote, then aggregate the results of each vote, and only at the very end of the tally decrypt the votes. So that allows us to like aggregate the votes, count our votes, even though they are encrypted, but only at the very end decrypt the votes. So like there's no information leakage. An example for that could be El-Gamal. There's something called, I think it's being called exponential El-Gamal, which is allowing you to do like the addition over encrypted data. If you're interested there, I've also linked 2 links. A detail, like a post going into detail about homomorphic encryption and like sort of like a very basic implementation. And if you're still like interested into a voting application, like how one would actually implement that, a while ago for our integration tests in the snark.js code base, we implemented a on-chain voting application. It's running as an integration test, so you like can take a look, just click on the link, and yeah, if there's like some, I guess like implementation questions that we couldn't get into, you can just take a look yourself. So I think that's it from our side, and I guess now it's time for questions. Thank you.
Maybe to kick it off, there were a few questions in the chat about the nullifiers in our architecture and how you would actually retrieve them. I have to admit we added the nullifiers pretty late, so Florian had them in the advanced section, and I said, yeah, we should have them everywhere because users can vote many times otherwise. So we kind of added them a few minutes ago. So there's a couple of things missing, I guess, in the description. How these nullifiers get into the smart contract, and how we check that they aren't included yet. So what should actually happen is that you have some wallet with your private key in it, and that wallet should have a method to create nullifiers. Okay, so this is not shipped right now, but actually we're working on that. So it should, or the smart contract should be able to ask the wallet for a nullifier, and it will pass on a certain message that is connected to that nullifier. So it will be for the specific voting procedure, for instance, and then you would there would be a pre-built zkApp method to verify. So that part would be covered. And actually, 2 weeks ago, I wrote an RFC for how this could work in zkApp. I'm posting the link in the chat if anyone is interested. So that covers how we actually would create the nullifiers. And then there was the question, well, where is this Merkle tree stored? Because nullifiers would be in the Merkle tree, and we only store the Merkle root in on-chain state. So we didn't cover that part in the architecture, except in the off-chain version. But this nullifier Merkle tree, that would have to be stored by some service, which, or by yourself, I don't know. But there would be it would have to be off-chain storage that you can fetch, that you can fetch to use the Merkle proof in your smart contract. So that there would be some additional service where you ask for Merkle path to your nullifier, and then you would get it and would pass it to the smart contract. Yeah, that's it. Does this answer the questions?
Looks like there's a couple other ones in the chat. Gregor? I could point to one from Mario. What would be examples on how to verify later that a given proposal got more than N votes?
So I guess if you specify a list, like if you have like some rules guarding who can vote, you then can prove that only a subset of all eligible voters can vote. So you can already make sure that there is no proposal with more votes than there should be, unless there's a bug in your system. But maybe you can clarify your question so I can like better answer it. But yeah, I'm a bit unsure what you mean by proving that you can like verify that there are more than N votes. So maybe you can clarify that.
Yep. Do you hear me now?
Yes.
Okay. What I meant is, for example, you made, it was a proposal, it was voted, and so the proposal got 100 votes and 70 positive votes. Okay. So, for example, to be approved, the proposal would need, for example, more than 60% of the total votes. That will mean 60 votes, more than 60 votes. So how can you generated a proof that the votes were counted, but how do I, is there a method called, how do I develop some small function that I say I can check that this proposal had more than 60 votes, for example, because the proof is there. How do I verify an existing proof So what you have shown is how to create the proofs, but how do I run a verifier on that proof? For example, has this proposal got more than 60 votes? That would be the question, okay? Is it clear now?
Yes. So
Thank you.
the verify in our system would always be the Mina smart contract. So if we have like all off-chain votes, and then we would verify the votes on-chain in a Mina smart contract using the sort of like verify proof method. In that method, we could specify that, say, okay, every proof has a public input, and the public input could then be the result of the outcome. And then we could say, okay, if sort of like yes votes, or like, well, you could say if the sum of yes, no, and abstained is bigger than 60, then we say, okay, the proposal passed. Else, the proposal didn't pass, right? So that is something that we can then do on-chain. As soon as we have the final result, we can then do some action based on whether or not the proposal has passed or hasn't.
Oh, so you will store the result of the proposal in a state variable inside the
Yes.
contract. That would be, and so I will check the state of that variable.
Yes.
Okay. Okay. Thank you.
And if you don't trust some GraphQL relayer that it gives you the correct state, then you can run your own Mina node, and you will verify the proofs yourself.
Directly in the browser.
Looks like there was one more from Vasco, who's asking if asking to confirm that homomorphic operations can be implemented within Snarky.js.
Oh, sorry. Yes. There are different schemas of doing it. Currently, I implemented a very basic partial morphic encryption using the Algamal algorithm, which is relatively straightforward and efficient. You can do it both over a normal finite field, as well as over an elliptic curve. But I think from my research, if you do it over an elliptic curve, you can't, there's no bijective function that maps sort of like integers, or like plain text to group elements, to curve points and back. So I think that doesn't work, but you can implement it over just like a finite field, which works. There are things that are a bit inefficient, of course, using like finite fields and some operations, but you can do it. If you want to be if your scheme should be additive over the plain text, then you have to use a few tricks. For example, you, instead of encrypting the message directly, you would have to raise the generator of the group to the message, and then encrypt it, and then decrypt it, trying using lookup tables, but that's too in-depth. It should work. There's like sort of like nothing to that prevents you from doing it. It's just like a question of, is it efficient enough? Does it make sense? And is it secure? Of course, but you can pretty much implement pretty much everything.
So I might want to add that many of these cryptographic schemes are defined in terms of finite fields and elliptic curves. So you will find many schemes that just require an elliptic curve and operations on it. And we have a finite field and an elliptic curve built in natively into our proof system, and operations on it are reasonably efficient inside the snark. So that what makes it realistic to, let's say, do encryption inside of one of our snarks.
Fantastic. Do we have any other questions? Don't be shy. It's a great opportunity. Yes, Mario.
Okay. Sorry for being so questioning today. You mentioned in your previous answer that you can also run a Mina node to just do the proving yourself. Does it have sense to run your own Mina node? I think it's much more. It has much more sense to have confidence in the public Mina nodes and the public Mina validators that are running nodes. So I don't just have to run my Mina node to just verify a proof. Is that right? I'm mistaken in what I'm talking about. I just didn't understand fully what you mentioned by running your own Mina node to just verify your proofs. That would be something like having a private chain. That's what you meant?
No, that would be like participating in the Mina chain.
Okay. Okay.
But
Well,
you're
I'm
right.
running. Okay.
Yeah,
No,
probably most people won't.
I'm running validators on other chains, so I will be interested in running a Mina node, but it's different from developing for Mina. That I see
Can
two
people hear
as
me?
different things. Okay. Okay. Thank you.
Yeah, I agree. Most developers probably won't run their own nodes, but I just wanted to say, if it's a high stakes application where it's really important that the application developer trusts the process, and maybe he runs his own node because that way the developer can guarantee that this is the true state. So if it's a very important application.
Okay, understand. So it would be some just like a means of guaranteeing that you will you will always have a node which can process the application requirements. Okay, that would be something like idea of running your own node.
Yeah.
Okay, got it. Thank you.
Okay. Last call for any questions.
Hi there. So I'd like to ask a question related to this kind of nebulous, maybe get the gist on the stability. Like I noticed in the slide about the zkApp program that the library is experimental. I'm already expecting we're going to evolve with the ecosystem as it's developing, as far as like moving towards production, or if we invest into a certain developmental direction, how stable is it, or how developing is it?
So the reason zkApp program is experimental is mostly because we weren't really we wanted to try out a different style of API, which is different from smart contract, and we didn't really settle for one of them. And also there are a few DX things that we really could improve in zkApp program. But I mean, it doesn't work. It doesn't mean that it doesn't work or something. I think the functionality is pretty stable, but the surface might change for this particular feature.
Okay, cool.
I think it's also important to mention that the recursion itself is currently running on the Berkeley testnet, and like the entire zkApp smart contract layer is using You hear Florian? Or
I don't hear it. But I guess he wanted to say what zk program does is really what Pickers does, and it underpins all of Mina. So it's very much not experimental.
Yeah, I lost internet
It
connection
used
there.
it's used all over the place. Yeah.
Thank you.
Can I ask a question? Cool. I wonder, is it reasonable to use Mina blockchain for creating dApps like Instagram or Twitter, where people can share their photographs or like short messages? Is it reasonable to use Mina blockchain for such kind of applications?
So in theory, Mina, so like you can do pretty much everything. Considering that the smart contract layer is like functionally complete, you can do like a lot. You can like sort of elevate your application using off-chain. You can then like prove sort of like actions off-chain. But it's also important to mention that you can't store images, for example, on Mina. You also can't store tweets. So Mina is like sort of, if you're planning on building something like that, I would consider Mina to be more like a settlement and verification layer instead of a storage layer, if that makes sense. So I mean, it's possible, but it sort of like depends on what exactly you want to do and how you want to structure your overall application. So yeah, that's my opinion, my take.
But for example, how Entity works on another blockchains. For example, I can store image on IPFS network, right? And maybe during the transaction, I can store short link for the image itself on the Mina blockchain, right?
So you could, for example, use a Merkle tree and then reference that off-chain data to IPFS. That could be possible. So yeah.
Got it. Thanks.
Yeah, or you could store a link that's like an NFT. You store it on other blockchains. You could do that on Mina as well.
I have one other question. Can I share my screen for a second?
I don't know. Is that possible?
I'll try if it's possible.
I guess if you have like very in-depth implementation details, like how to use Snappy.js, I would recommend to use the Discord and to ask that question there. It's probably more efficient.
Okay, thanks.
Looks like we have one raised hand from Nin.
Hey guys, hello. I'm new to zkIgnite completely, and from my understanding, just let me know if it's correct. A voter goes to the voting app, they verify themselves using an email. Are the electors right now limited to a One Labs email domains, or is anybody who owns a Mina token, are they able to vote?
Oh, I can jump in. I think this voting application presentation actually doesn't have anything to do with zkIgnite as a program. This is completely independent as an example for architecture. And the electors for zkIgnite who have come on board are not members of O1 Labs. They're actually members of, well, there could be, but in this case, this for the sake of anonymity, I won't say who exactly they are, but they are from members across the Mina ecosystem. And we're using a kind of purpose-built platform for the voting, and we'll cover how like the voting works in about 2 weeks when the voting period begins. But it will be the electors who are voting, and there's 15 electors per track.
Cool, thank you. I was like super confused.
No, no worries. Yeah, this is, yeah, no, thanks for clarifying. Okay, do I see, do we have any? Yes, I think we have time for one more question and then we'll finish up with some program details. Mario, do you want to go for it?
Yeah, if there is no other question, for example, if imagine you will have a DAO, and the DAO will have multiple proposals. Okay, so what you presented here is just an example of an architecture for one proposal. In the case of a DAO having multiple proposals, would you have one zkApp account per proposal linked to one zk account for the DAO, or you will have all just one account and all information in that account? There are two different architecture schemas, so just curious about that. How would you do that?
Yes. So you are correct that at the moment we are only like we have one account for one proposal. That's also why we had the unique proposal ID. If you are like a big organization running 10 proposals a day, you could as well just like use one dedicated account for proposals. That can have its benefits. For example, you can then sort of like request the data from like a specific proposal account. But you could also have one main account that collects all, like that sort of like reference all off-chain proposals and then like sort of keeps a Merkle root of all proposals off-chain. That could happen as well. I guess that's simply a trade-off what you want to do and what you are willing to develop. If you go like if you choose the second variant with having one central settlement contract and then many off-chain proposals, then you have to like run more and more off-chain infrastructure, right? You need to like sort of, yeah. So I guess you can do both. It's a question of what you want to do and what your trade-offs are.
Okay, thank you very much for everything. Okay.
Definitely, thank you.
Do you see my screen now?
We do, but I'm really sorry, but we have to wrap up the presentation. Is it okay if we take this to Discord?
I'm sure. Sorry. Okay.
Oh no problem at all. Just bad on too bad on the timing, but we'll see you in Discord. And thanks for asking the questions. Before we're going to hand it over to Janae to talk about program details, but before we do that, I want to give a huge thanks to Florian and to Gregor and some of the other team at O1 Labs for putting this presentation together. This was really, really helpful. And all of this material will be recorded and sent out afterwards as well. So you'll be able to access the links, which are their own treasure trove of information. So if we can just do like virtual round of applause for these guys. Really, really helpful. Show some love in the chat. Cool. With that, Janae, I'll pass it over to you to close us out with some next steps.
So many screens going on right now. So hold on one second. Am I good?
Yep.
Perfect. All right. Well, let's talk about next week. So next week, we're going to be featuring all of our proposals, featuring you, cohort 1. So we're going to be doing proposal presentations. What does that entail? Basically, if you remember, I think it was a week or so ago, we had some people from cohort 1 showcase themselves and highlight what they were working on. And we're going to be doing the same kind of format where you will be able to come on camera, talk us through your proposal, and ask for some support from your peers. These presentations will be about 3 to 5 minutes long, and you will just state your problem and then your ideas, and highlight one area that you would really love feedback on. And this is just because we received so many proposals. It was incredible, but we wanted to make sure we had time to go through everyone's and give them the chance to highlight this. And we will be doing this in 2 different sessions. I will also be sharing more information later on today and throughout the week. So make sure you're checking your Discord, you're checking your email to get the actual signups so that you can present and a deeper understanding of what you should be presenting during this time. I'm going to pass this over to Alex.
Sweet, thanks, Janae. Yeah, so as you're working on your proposals, we figured you might be looking to expand your team outside of the cohort. So we actually created a couple of custom ZK Ignite cards that you can share on social, LinkedIn, kind of wherever builders are in your network. There's cards for the zkApp and the Dev for Dev track. And you can download them from the shared Google Drive folder that's linked on this slide. I'll also make sure to send everything on Discord, so it's handy there. We also have a pre-built tweet format that if you'd like to use that, it'll be linked. Just make sure that you customize your message in the tweet and then attach the image. But yeah, if you have any questions on any of this, feel free to reach out on Discord. I'll send that note shortly after this meeting.
Awesome. And so our last thing that we want to say before we end the meeting, we will be opening our Gather Town. If you want to take any of these conversations, any of these questions, any of your thoughts over to another space, Gather is open until for a couple of hours today. We hope to just have you all sit around, engage with one another, and just, have a little fun. I did add a little bonus room if you can find it. It is castle themed, so please check it out. And that's it. I will pass it back to Will in case if I didn't cover anything, and close this out.
Cool. Thanks, Janae. And yeah, it's I think with the Gather, just so everybody's on, like, we're continuing to experiment with it, but like we just want to we're going to make these spaces available after every call. So if you want to just like find a shared virtual space with anybody else here, just like send them a message, and that link is kind of yours. We're kind of moving away from like programming Gather as much as it is just a space for you to kind of come and hang out. I'll also say when it comes to like the feedback stuff, if people have ideas, or like if there's things that you all want to experiment around, like more rapid pitching or sharing, or ways to kind of like get feedback on your proposal, and you want to kind of try something with Gather or try something in a group format, we're also super game to like experiment with you. So hit us up on Discord, just in the channel, if like you have some ideas around ways that we can kind of increase the feedback loop with the proposals. And we still have 2 weeks to kind of or a week and a half to get them, or 2 weeks, sorry, 2 weeks to get them updated. So it's been a pleasure thus far to see everything come through, and to get to work with and collaborate with you guys, and very much looking forward to what the next couple of weeks have to offer. So with that, rock and roll week 4. Thanks again, Gregor, Florian, see like Jason and Brandon and Nick, and from O1 in the chat as well, and Regina, Yoni. Thanks for making this week very fruitful. And we'll talk to you guys soon.
Bye-bye.
Bye, everybody.